Um, yeah, hello everyone. Today will be live coding in my WSL, right? So we'll open this instance here. Yeah, lean for theorem prover. Theorem proving in lean for. Uh, NVIDIA lean for a stream. Hello everyone. So today we'll be streaming in my Theorem prover Lean 4, right? I did last stream where I set up my Lean 4 Theorem prover, right? But now I will be doing some basic propositional logic in my stream. Yeah, so if yeah, nobody in chat, so that's fine. Yeah, so first we can do this in theorem proving first. For Lean 4, we need to initialize a project, right? If you are familiar with the Rust programming language, in Rust we can initialize the project using cargo, right? Like I don't have Rust here, but for example, Rust or cargo is not in my path to enable. So like that, we can initialize a project using Lake, right? So this is Lake, and Lake is installed. In my last stream, I set up the theorem prover Lake, right? Lean. So Lake is a Lean's package manager. I'm hoping to do a lot of stuff, right? So you can see Lake is installed, but it's not like working properly, I guess. So I can do Lake new package name, right? So since I'm doing propositional logic, I will do prop. Package name is prop, and it will initialize the new project, right? So this is the Lake project, and it will initialize the new project using Lake, and I can do like yeah. Okay, so I don't know why they enforce that I need to have git, right? Hx configuration.nix. So I need to add git now to the packages, right? Oh my god, git. This is not good. Yeah, sudo next is rebuild switch flake.slash. So I need to rebuild my Nexus configuration now because I don't have git. Usually I stream, I want to set up a stream where I can use my Linux, right? Linux OS, but I am not using the Linux, right? So I just stick with this. So yeah, we'll do some proofs, and in Lean 4, these are the example proofs. So I'm installing Git. So yeah, Now you can see I'm installing Git, right? So hopefully, yeah, not like in last stream where I spend my whole stream. Yeah. So normally when people do streams, they usually do it when when they have like communication. But I'm talking in the stream because I want to eventually also capture videos during my stream and also just post those videos like a knowledge base, right? So people can just have the videos up, and if someone wants to learn lean later on, they can just do the learning. So Git, when the Git is installed, I think Lake should work. I think that's not good that Lake depends on Git, because Cargo doesn't. Like, you can, I don't know why Lake wants Git. I mean, it says that Git is not found. Maybe they assume that Git is like the basic thing that every system should have, maybe. But I think NixOS should also have that as a install dependency, right? If you are familiar with the concept of functional programming, in functional programming there is this concept called purity, right? So that means whatever program that you're writing should be pure, right? So I think NixOS also has this concept called purity, right? That means the OS should not have interference from outside world, right? It should be it should not be impure, right? So if you see my thing, right, my NixOS config, when I did this sudo nixos rebuild switch flake, I'm using a flake in my config. So the flake is always pure, right? The flake is always pure. That means it will be pure. So let's see. So now prop. Oh, it created it. Nice. Okay. Now we can do main.lean, right? Or yeah, main.lean, and we can just write proofs in this. So yeah, now we will be doing the proofs, right? So this is my NixOS. Unexpected token prop. Interesting. Okay, why is it saying so? Prop.lean. Let's see. I think maybe I'll just write my proofs in prop instead of main, right? So import prop.basic. That's nice. So let's just do what. Why is my LSP not working? Type of variables. Here PQRR type of prop, right? You can just do the proof example, right? Example P and Q, right? And F, Q, and P, right? I'm sorry. So yeah, declaration uses sorry in the sense that the proof does not exist. I'm just saying sorry, right? So there are different ways of writing the proof, right, here, and I can use lambdas, right? If you are familiar with functional programming, in functional programming there is a concept called lambdas, right? So you can do the same here, right? So currently I can just say sorry, right? And I can also write other proofs, right? By I can also give names to my proofs, right? So yeah, so we can also do like simple proofs, right? Currently I'm doing by implication here, but I'll just say that I just want to prove implication, right? That makes it easy. That makes the proofs easy. But because for the beginners it is easy, I can just use lambdas to denote my proofs. So yeah, let's do that, right? So lambdas are nothing but function application, right? So I can do this as well. Fun of x, that is of type p and q, right? Now there's this function, right, that takes an argument of type p and q, right? That doesn't take p and q itself, but it takes a argument of type p and q, right? If you're familiar with type theory, right, you can do this, right? Then now what does it do? It needs to give q and p back, right? That's what we are trying to prove here. So now to give q and p back, it needs to the uh, apply the and introduction rule, right? So in Lean there is and dot intro, right? This is the constructor. So here if you give a and b, it gives a and b back. So we'll do that, right? And dot intro, applying the constructor arguments. Now we need to get q and p somehow, right? How do you get q and p, right? We can do x dot right, uh, right, right. That's one value, x dot left, right? Yeah. So that's simple. That's how the proof is done. Yeah, it is showing me with this little thing of how that proof is complete, right? That's one proof. Now we can do the same for q and p, and q and p implies p and q, right? We can do the same, but right now we'll do a different notation now, right? We can do the lambda notation, right? Lambda x of type q and p, right? We can do the same and dot intro, right? Now x dot left, or x dot right, and x dot left, right? Yeah, simple. So now we proved both, right? We proved p and q and p both. Now we can combine, we can give this example some name, right? First, right? Or I think we can't do that. We have to say it a lemma maybe, or theorem, right? Theorem, yeah, because we can't name uh, theorem, right? Theorem second, right? Now we have two theorems. Now we can prove the original goal from the example. We can also say we can say example p and q yeah, p and q if q and p, right? Now we need to prove them, right? We can do if dot intro, right? We can do if dot yeah, if dot intro, this is the constructor, and now we will just say first, right, and second, right? We can just say that. Right, we need to do second and first, right? Second and first. Interesting. Why is this not taking these arguments? Type q and p. I mean, that makes sense, right? For me, why is this wrong? Why is this wrong? Hmm. This is interesting that it says that it is wrong, right? Uh, okay. Uh, why is this wrong here? I mean, PQ probe has, wow, this is mind-boggling that Lean does not accept this proof. Maybe I need to just name it a theorem. Uh, theorem third, first and second. Ah, wow, 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 wow. Maybe I'll just remove this. Oh, no. Oh God, that variable declaration, right? That's not. Now we can do another theorem, right? We can do other properties. Maybe we can do the theorem fourth. Fourth has, we need to prove P implies Q uh, implies R, right? So I need to put brackets if Q and P and Q, P and Q implies R. Sorry. So this is now a big proof, right? Now we can just start proving this, right? So we can do the same, right? Like we did for the previous one. I can just say that this is implication, right? And we can do proof where we just apply the function application. We'll just say that, okay, now I have a lambda, right? I have a lambda that is of type P, that takes a type of P implies Q. Yeah, P implies Q implies R, right? Because lambda is function application, we can do this. And now it needs to give me P and Q implies R, right? So we know that P and Q implies R is nothing but, so here we need to also be very careful about the precedence of the bindings or construct or bindings, right? So here the implication is weak, right? Implication is weak binding, right? That's very important. So if implication is weak binding, then P and Q is strong, implies R, right? Now we need to do the construction of implication, right? That means we have to do implication introduction rule. We need to do implication introduction on R, right? And we need to do implication introduction on yeah. So to prove P and Q implies R, we just need to do that. We just need to say that we just need to apply the same rule here again. So we'll just say lambda, right? Now this is some k, right? It's of type p and q, right? And it should give me some r, right? Eventually. So now we have r. We need to get to r, right? So how do we get to r, right? Now that's what we need to think. So to get to r, we can do a lot of things, right? We have p implies q implies r with us, and we have p and q with us, right? And we can also do the proof of maybe we can do like p, or we can do, for example, modus ponens, right? If we have just r, right? We need to prove r, right? So to need to prove r, we need to do modus ponens, right? So that means we need to prove q, right? And we need to prove also modus ponens is nothing but implication, right? Implication, or if, or no, implication. Yeah, interesting. How do I get that? Elimination, modus ponens. Modus ponens. Interesting. If dot ln, but this is elimination of a implies b, or a double implies b, right? Interesting. But how should we do modus ponens? Interesting. Application. There's and, there's or, right? But why isn't there modus ponens? Oh, interesting. Okay, how did they do the modus ponens? Logical equivalence, negation, falsity, disjunction, conjunction. Okay. Propositional logic, right? Propositional logic, not, and that's nice. Conjunction, disjunction, negation, falsity, logical equivalence, right? Subgoals. Interesting. So this is if dot intro, right? But we don't need if dot intro because if is logical equivalence here. So we need implication, but this is negation and falsity, but we don't need this. To prove R, we need modus ponens. Interesting that they talked about the implication here. Let's see where we can. Yeah, you have the proof for something like you have a proof for something like let's do it like this. So P, right? P implies Q, right? and you need to prove both if you have Q. Fine. So that's what is opponents. So that means to prove Q, you just do this. Right? So to do that, if this constructor is just function application, you can prove P somehow, right? Yeah. So you have to get to R, you need to prove P implies Q. That is, you need to do the function application of Q. That means here you need to do another R, right? R is of type lambda R is of type R, right? And we need to get the we need to get the P and Q. That means we need to get Q implies R. We need to get that. We need to get Q implies R, right? Okay. Okay. We need to do this. So R and Q implies R. This is Q. Sorry. Q. Here we have to do R. Right? Okay. Whatever. So. Oh. So. Okay. This is tricky. I mean, for me, this is tricky. This is not easy. Formalizing logic is not easy. You have to practice a lot of formalization of logic. Then and only you can master it. If you master this kind of formalization, then you can, yeah, you can do anything, right? So for today, I will just finish this part, and I will then be ending the stream. And again, tomorrow I'll do for some time. So slowly I will improve gradually, right? So I hope, yeah. I mean, this is some high level stuff. Not everyone can do it, right? Yeah. So, I mean, I watched the YouTuber Terence Tao, I think his name, right? He does a lot of proofs, right? He does like very nice proofs of things, right? So, yeah. I'm trying to also do like proofs on my stream with multilingual support, right? But let's see. Yeah, I can get q from k dot right, and here, right, I can do that. I can get that from k dot right. Here. So let's see. To get to that q implies r, we need both p and q, and we need to do function application, right? So implication is nothing but function application. So modus ponens is nothing but, yeah, proving q. Here to prove q, you can do the k dot right, k dot right. Yeah. Right. Yeah. And yeah, k dot right. Yeah, it's hard. This proof is hard. Like, I need to do a lot of propositional proofs like this. So I can be good at a lot of things. I'll do this.